Hello, hi everyone. Welcome to the class, students. So now we are discussing about current electricity. Current electricity. Okay. So welcome to the class. This is our Siva sir, right? Yes. So now I equal to Q by T. The rate of flow of net charge through a cross-sectional area is called electric current. So what is electric current? The rate of flow of net charge through a cross-sectional area is called electric current. Okay, I equal to Q by T, I equal to dQ by dt. dQ by dt. So dQ by dt is a instantaneous current. Current at the particular instant. Current at particular instant is called instantaneous current. Understood or not? So now 1 ampere is defined as 1 coulomb of charge flowing through unit cross sectional area per second. 1 ampere is defined as, so SI unit of current is ampere, SI unit of charge is coulomb, SI unit of time is second. Okay. Once again, SI unit of current is ampere, SI unit of charge is coulomb, SI unit of time is second. 1 ampere equal to 1 coulomb per 1 second. Okay. So that is electric current. Now, so 1 ampere is defined as 1 coulomb of charge flowing through unit cross sectional area per second. Right. Now, we can take first one. If the charge can be obtained by multiplying constant current and time interval. Constant current and time interval. And coming to the next one, so the flow of charge. So if the current is function of time, if the current is the function of time, then so flow of charge can be given. So delta Q equal to integral Ti minus Tf I dt. Coming to the third one, so the flow of charge can be obtained by area under IT graph. Okay, area under IT graph. So delta Q equal to area under the IT graph. Okay, IT graph. So that is the flow of charge. So you can observe I on T on. So this is the graph. The graph is flow of charge. The graph is flow of charge. Understood or not? I hope it is very clear. Next one we will discuss about. One more point, that is so based on magnitude and direction, current can be divided into two types. Based on magnitude and direction, current can be divided into two types. One is direct current, another one is alternative current. Based on magnitude and direction, current can be divided into two types. One is direct current, another one is alternative current. Okay, so magnitude and direction does not change with respect to time. Okay, so magnitude and direction does not change with respect to time. That is called DC current. So DC current is nothing but magnitude and direction does not change with respect to time. But coming to alternative current, Coming to alternative current, magnitude and direction change with respect to time. Magnitude and direction change with respect to time. Understood or not? So both magnitude and direction changes, we can say. So DC example, cell, battery, DC dynamo. So for AC example, AC dynamo. Is it clear? Yes. So next one we will discuss about, okay, here in this one more point is there, that is if the charge is flowing in a circular path, if the charge is moving in a circular path, you can observe this. So charge Q is moving in a circular path with the frequency F. The charge is moving in a circular path with frequency F. The current can be written psi equal to QF. Okay. So current. So when we can say current is flowing, when charge is moving in the conductor. Okay, when charge is moving in the conductor. So charge will, so only one electron, only one positive charge, one negative charge moves. Will you say current is flowing? No, we can't say like that. There are number of charges are moving in the conductor. Number of charges are moving in the conductor. Then only we can say current is flowing. So charge is a quantization. So charge is quantization. So Q equal to plus or minus NE. Q equal to plus or minus NE. Quantization of charge. Quantization of charge equal to Q equal to plus or minus NE. So N is number of. So here positive charges are there, negative charges are there. Positive is proton, negative is electron. Okay. So Q is the quantization of charge. Q equal to plus or minus NE. Plus or minus NE. Here one more point. On one electron, 1.6 into 10 power minus 19 coulomb. In 1 coulomb, 1 by 1.6 into 10 power minus 19 you can take. Okay. So you can observe here 10 power minus 19. Then that can be written 1 by 1.6 into 10 power 19. Then you'll get, if you solve, you'll get 0.625 into 10 power 19. Then you'll get 1 coulomb 6.25 into 10 power 18 electrons. In 1 coulomb 6.25 into 10 power 18 electrons are present. Understood or not? So I hope it is very clear. So just check once. On 1 electron, 1.6 into 10 power minus 19 coulomb. In 1 coulomb, 6.25 into 10 power 18 electrons are present. So understood or not? So that is about AC and DC and remaining points. Next one we will discuss about one more, drift velocity and relaxation time. Drift velocity and relaxation time. Drift velocity and relaxation time. Okay. Drift velocity and relaxation time. So drift velocity and relaxation time. When electrons are moving in the conductor, experience force. So here you can see current is moving like this. So electrons are moving in the conductor. If the electrons are moving in the conductor like this, okay, so it experience force. Okay, it experience force. So it produces acceleration. Acceleration. Understood or not? So that it produces acceleration. Produces acceleration. That is F equal to E is the electric field. So F equal to E or QE. Now, so when it experience force, automatically that force will produce acceleration. Then F equal to ma. Then ma equal to E and QE equal to A equal to E by m. That is nothing but QE by m. Okay. So what is the drift velocity? The average constant velocity of an electron moving in a conductor is called drift velocity. Drift velocity. Coming to relaxation time. Relaxation time. So when electrons are moving in the conductor, one electron will hit another electron, that electron will hit another electron. Like that, keep on bombardment takes place. Keep on collision will take place between one electron to another electron. So the average time between two successive collisions. Okay. So here collision will take place again. Here collisions will take place. The average time between two successive collisions is called relaxation time. Okay. So this is about drift velocity and relaxation time. This is about drift velocity and relaxation time. I hope it is very clear. Understood? So next one we will discuss about current and drift velocity. 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 Drift velocity. Current and drift velocity. Okay. So when electrons are moving in a conductor, so this is the conductor. So the area of the cross section is A. Area of the cross section, and here also A. Then this is the length of the conductor. Okay. So electrons are moving in the conductor, right? Okay, see here. So electrons are moving like this. So drift velocity. So current is moving in this direction. Now we can observe, so velocity equal to displacement by time taken, or length by time taken. So Vd into delta t. So that is L. So that is nothing but Vd into delta t. So what about volume? Volume of this conductor. Volume equal to length into area. Length is nothing but Vd into delta t into A. Okay. So what about number of electrons present in the particular volume? Number of electrons present in the particular volume, that is nothing but, so here we can see N into Vd into delta T into A. So now delta Q equal to N Vd delta T into A into E. Now current I equal to delta Q by delta T. That is nothing but N Vd delta T into A into E by delta T. So we can cancel delta T into delta T. So we can cancel this too. So then I equal to N E A Vd. So we know current density formula. Current density equal to current density J, that is equal to I by A. So what is I? So NEA VD. So now NEA VD by A. So A get cancelled. J equal to NEVD. Okay, I hope it is very clear. Understood or not? I hope it is very clear. Is it clear? So next one. So we'll discuss about resistance and resistivity. Resistance and resistivity. So resistance and resistivity will discuss. Resistance and resistivity. Next one is resistance. So resistance is nothing but phenomena of opposing the electric current. So resistance is nothing but the phenomena of opposing the electric current in the circuit is called resistance. Okay. So resistance is directly proportional to length of the conductor, and resistance is inversely proportional to area of the cross section. R is directly proportional to L by R equal to rho into L by A. So rho equal to RA by L. That is the resistivity. Okay, I hope it is very clear. Just check once here. Now, so resistance, SI unit of resistance is ohm, SI unit of resistivity, and coming to resistance, it depends on length and area of the cross section, and resistance depends on temperature, and resistance depends on nature of the material. Nature of the material. Understood or not? Nature of the material. Is it clear? So coming to the resistivity, we can see, so resistivity, SI unit of resistivity is, so SI unit of resistance first, SI unit of resistance is ohm, SI unit of resistance is ohm, SI unit area is meter square, SI unit of length is, so SI unit of resistivity is ohm meter. SI unit of resistivity is ohm meter. Understood or not? I hope it is very clear. Just check once and you can observe. So ohm meter, and we can take ohm meter symbol, and the resistivity depends on temperature. Resistivity depends on temperature, and resistivity depends on nature of the material. Nature of the material. Understood or not? I hope it is very clear. Just check once. Just check once. These are the points. These are the points. Okay, resistance is directly proportional to length of the conductor. Resistance is inversely proportional to area of the cross section. R is directly proportional to L by A, R equal to rho into L by A. SI unit of resistance is ohm. So symbol and resistance depends on length and area of the cross section. Resistance depends on temperature. Resistance depends on nature of the metal. Whereas resistivity, so SI unit of resistivity is ohm meter, and resistivity depends on temperature, and resistivity depends on nature of the material. Okay, so I hope it is very clear. So this is about resistance and resistivity. So now we will discuss about temperature dependence of resistance. Temperature dependence of resistance. So we'll discuss those points also. So we'll see. Temperature dependence of resistance. Now you can see temperature. So if you observe one thing, so when temperature increases, the free electrons in the conductor also increases. So the free electrons in the conductor start moving. Yes or no? So because of that reason, when free electrons start moving, or ions of the conductor start moving, okay, ions of the conductors is start moving. Then what happens? Immediately conductivity increases, resistance and resistivity decreases. Here you can observe. Simply we can say electrons are start moving. So electrons will vibrate with greater amplitude as temperature increases. So immediately as temperature increases, electrons are moving with a higher amplitude. Then at that time, resistance and resistivity decreases, conductivity increases. When electrons are moving with a greater amplitude, these electrons will hit another electron. Okay, electrons will hit. So collision will take place. Yes or no? So bombardment will take place. Collisions will take place. Then what happens? So within the one place only, the collisions will take place. Electrons are not moving forward. That time resistance and resistivity increases. Conductivity decreases. Okay. So by this we can conclude that temperature increases, so resistance and resistivity also increases. Resistance and resistivity also increases. Understood or not? Now you can observe here. So R is directly proportional to L. R is directly proportional to L. R is directly proportional to L. R is inversely proportional to area of the cross section. R is directly proportional to L. So R equal to rho into L by A. Understood or not? So when temperature increases, resistance, length and area of the cross section also increases. When temperature increases, length and area of the cross section of the material also increases. So observe carefully. When temperature increases, length and area of the cross section of material also increases, right? But actually these changes are quite small. That's why L by A is constant. R is directly proportional to rho. Okay. So R is directly proportional to resistivity we are taking now. So R T equal to R naught 1 plus alpha into T minus T naught. Then RT equal to R naught plus R naught alpha into T minus T naught. Then RT minus R naught equal to R naught alpha T minus T naught. Then alpha equal to RT minus R naught by R naught into T minus T naught. So alpha is the temperature coefficient of resistance. Alpha is the temperature coefficient of resistance. Understood or not? Yes or no? Now by that we can also write alpha equal to rho T minus rho naught by rho naught into T minus T naught. So here alpha is the temperature coefficient of resistivity. Understood or not? I hope it is very clear. So these are the points. These are the points related to temperature. So now we will discuss about Ohm's law. Okay. So Ohm's law is nothing but Ohm's law. So now we'll discuss about Ohm's law. Ohm's law. So Ohm's law is nothing but the potential difference. Ohm's law is nothing but the potential difference across the ends of the metallic conductor. V is directly proportional to I. V equal to IR. V is directly proportional to I. V equal to IR. So V is directly at a constant temperature and physical conditions also same. So the potential difference across the ends of the metallic conductor is directly proportional to current flowing through it. At a constant temperature and physical conditions also same. So V is directly proportional to I. V equal to IR. Okay. R equal to V by I. R equal to V by I. So if you draw the graph for V and I, so V on y-axis, I on x-axis, the graph is straight line starting from origin. The graph is straight line. Yeah, definitely. Just now I explained. So temperature increases, automatically resistance and resistivity also increases. Okay, so now this is the theta. Now you can observe slope. Slope equal to tan theta equal to R. Tan theta equal to R. Slope of the graph is tan theta, that is equal to R. Okay. So now you can see. Now you can observe. So R equal to V by I. So one is for ohmic conductors. Ohmic conductors, and second one is for non-ohmic conductors. Non-ohmic conductors. Okay. So this is for ohmic conductor. The conductors which obey Ohm's law, those are called ohmic conductors. The conductors which does not obey Ohm's law, those are called non-ohmic conductors. The conductors are circuits or materials. Anything we can say, the conductors which obey Ohm's law, those are called ohmic conductors. The conductor which does not obey Ohm's law, those are called non-ohmic conductors. For non-ohmic conductor, the graph is curved. Okay. For non-ohmic conductors, the graph is curved. So you can observe here. This is for non-ohmic conductors. So here you can observe V1 and I1 here. V2 and I2. I2 and V2. So here it is P. This is P and Q. Okay. So now you can observe. So R1 equal to V1 by I1, that is at P, and R2 equal to V2 by I2. V2 by I2 at Q. V2 by I2 at Q. Okay. So R1 is not equal to R2. Okay. So R1 is not equal to R2. Okay. So I hope it is very clear. Once observe. So ohmic conductors, the conductors which obey Ohm's law, those are called ohmic conductors. The conductors which does not obey Ohm's law, those are called non-ohmic conductors. Okay. So I hope it is very clear. Understood or not? This is about Ohm's law. Next one. So we'll discuss about electromotive force. Electromotive force. Electromotive force. Electromotive force. Electromotive force. Understood or not? Normally, you can see here, this is the cell and this is the resistor. So current is passing like this. Okay. So when you connect the cell, anyway positive charge will move from positive terminal to negative terminal. So positive charge will move from positive terminal to negative terminal. We know that. Whenever we connect the cell to the circuit or battery to the circuit, so charge will move from positive terminal to negative terminal. Like nothing but high potential to low potential. So charge will move from high potential to low potential. So when it is there at a negative terminal, so here, when positive charge is there at negative terminal, that is nothing but low potential to high potential. So inside of this cell, okay, the work done to bring, you need positive charge. So positive charge from lower potential to higher potential, or negative terminal to positive terminal, or the force which is used to move the positive charge from negative terminal to positive terminal inside of this cell, or the influence that make the positive charge to move from low potential to high potential, negative terminal to positive terminal, that is called electromotive force. Electromotive force. Okay. Or simply we can say E equal to W by Q. E equal to W by Q. Electromotive force. Understood or not? So the force which is required to move the positive charge from negative terminal to positive terminal, or low potential to high potential, so in the cell is called, or work done by the cell on the charge is called electromotive force. E equal to W by Q. E equal to W by Q. So I hope it is very clear, right? Next one. So we will discuss about Resistors are connected in series combination. Resistors are connected in series combination. Resistors are connected in series combination and resistors are connected in parallel combination. Okay, so we'll discuss those points. Resistors are connected in series combination. Resistors are connected in series combination. Okay, series combination. Resistors are connected in series combination. So check once here. Now you can observe 1, 2, 3. Okay, ammeter. So here you can see battery. So R1, R2, R3, across R1, V1 I am connecting. Across R2, V2 I am connecting. Across R3, V3 I am connecting here. Okay. So now, if resistors are connected in series combination, so current is same throughout the path. Understood not? Current is same throughout the path. Then Is equal to, so positive, negative, Is equal to I1 plus I2 plus I3 plus, oh sorry, current is same, right? If it is same, so we have to use equal, right? Yes or no? So Is equal to I1 equal to I2 equal to I3 equal to I. From Ohm's law, V equal to IR. From Ohm's law, V equal to IR. Understood or not? From Ohm's law, V equal to IR. That is nothing but Vs equal to V1 plus V2 plus V3. So we can write IRS equal to IR1 plus IR2 plus IR3. So I am taking common. So I am considering common R1 plus R2 plus R3. So you can observe. So I get cancel. RS equal to R1 plus R2 plus R3. If resistors are connected in series combination, if n number of resistors are connected in series combination, if n number of resistors are connected in series combination, okay, so Rs equal to Nr if n number of resistors are connected in series combination. So normally formula is Rs equal to R1 plus R2 plus R3. Now, so we'll discuss about resistors are connected in parallel combination. Next, so we'll discuss about resistors are connected in parallel combination. Resistors are connected in parallel combination. Resistors are connected in parallel combination. So here you can observe So across R1, R2, R3, I'm connecting V. So if resistors are connected in parallel combination, so potential difference is same. If resistors are connected in parallel combination, potential difference is same. Yes or no? Now we can say so Vp equal to V1 equal to V2 equal to V3 equal to V. So V equal to IR. So V equal to IR. Yes or no? Now by that we can write. So IP equal to I1 plus I2 plus I3. Current is different. Potential difference is same. But current is different, right? So that's why V by Rp equal to V by R1 plus V by R2 plus V by R3. Now I am taking V common. 1 by Rp equal to V I am taking common 1 by R1 plus 1 by R2 plus 1 by R3. So V get cancelled. So 1 by Rp equal to 1 by R1 plus 1 by R2 plus 1 by R3. So this is about resistors are connected in parallel combination. If n number of resistors are connected in parallel combination, so 1 by Rp equal to n by R, Rp equal to R by n. Okay, so if n number of resistors are connected in parallel combination, okay, if n number of resistors are connected in parallel combination, if n number of resistors are connected in parallel combination, 1 by Rp equal to n by R, Rp equal to R by n. Understood or not? I hope it is very clear. So just check once. Right? So next one, this is about resistors are connected in parallel combination. Resistors are connected in parallel combination. Understood or not? Next we will discuss about okay. So many circuits can't be reduced. Many circuits can't be reduced into simple series and parallel. So in that case we will use Kirchhoff laws. That time we will use Kirchhoff laws. Okay, so we'll discuss about those laws. Okay. Which has the highest resistance in series combination? So Fazil, so you want to explain, okay? So here you can observe R1, R2, R3 are connected in parallel combination. So that is connected to the battery. So here potential difference is connected across R1, R2, R3. And now potential difference is same. So we know current is dividing I1, I2, I3. So IP equal to I1 plus I2 plus I3. From Ohm's law, V equal to IR. From Ohm's law, V equal to IR, I equal to V by R. So that we can substitute 1 by V by Rp equal to V by R1 plus V by R2 plus V by R3. So V I am taking common because in parallel combination, the potential difference is same. So in the parallel combination, the potential difference is same. That's why I am taking common. So 1 by Rp equal to 1 by R1 plus 1 by R2 plus 1 by R3. If n number of resistors, are connected in, okay, so if n number of resistors are connected in parallel combination, that is 1 by Rp equal to 1 by rp equal to n by r, rp equal to r by n. So we are taking common v value. So here and in this is there only, v will get cancelled. V value get cancelled, then 1 by rp equal to 1 by r1 plus 1 by r2 plus 1 by r3. Okay. So this is about resistors are connected in parallel combination. Resistors are connected in parallel combination. So as I mentioned here, so many circuits, so only few circuits, definitely we can understand whether resistors are connected in series or parallel, but some circuits may not reduce into series and parallel, simple series and parallel. That time we will use Kirchhoff laws. So Kirchhoff laws, there are 2 points are there. So there are 2 laws. One is loop law, another one is, first one is junction law, second one is loop law. So what is junction law? So we'll discuss about it. What is junction law? Junction law. So junction law we'll see. So Kirchhoff laws. There are 2 laws are there. Kirchhoff laws. Kirchhoff laws. Kirchhoff laws. Welcome, Fadil. Kirchhoff laws. Here first one is junction law. First one is junction law. Junction law. Second one is loop law. First one is junction law. So junction law is nothing but, so 2 laws are there. One is junction law, another one is loop law. Loop law. So junction law is nothing but the algebraic sum of all the currents meeting at a junction. The algebraic sum of all the currents meeting at a junction equal to 0. Okay, so now you can see. So I am taking this junction, and here I1, I2 and I3. Okay, so I1, I2 and I3 and I4. So here you can observe I1 plus I2 plus I3 plus I4. Sum of the currents reaching to the junction equal to sum of the currents leaving from the junction. Okay. Sum of the currents reaching to the junction is equal to sum of the currents leaving from the junction. That is about junction law. Coming to loop law here, so 4 points are there, very very important. So those we will discuss. So point number 1, so here I am taking the cell. This is the cell, so this is the point A and point B. So the positive terminal, negative terminal. So this is the path. So the path is very important, which direction you are going. If you are going from positive terminal to negative terminal, the EMF of this cell is negative. So you have to write negative EMF. And coming to the second one, so you are moving from negative to positive terminal of this cell. This is the path. Okay. Then EMF of this cell is positive. So you have to take positive EMF. And coming to the next one, third one. So you are going through across resistor. This is A and B. And you are moving along the current direction. This is the path direction. So there is a decreasing potential. That's why minus IR. Decreasing potential. Coming to the fourth one. So here you can observe fourth point. So if you are going across the resistor, so this is AB, so you are moving opposite to the current direction. This is the path. This is the path. So then there is an increase in potential. So that's why plus IR. Understood? So these points are very, very important. These points are very, very important. One is junction law, another one is loop law. In junction law, the sum of the currents reaching to the junction is equal to sum of the currents reaching away from the junction, leaving the junction. So entering the junction, leaving the junction. So entering the junction, I1, I2, entering equal to leaving junction, I3 and I4. Okay, so coming to loop law, so when you are moving from, so here you need to understand carefully, how to observe carefully, how to take the path in which direction you are moving. Okay, leave it about positive, negative. So take one point in the loop and select your path. Select your path. The dotted lines, whatever I am representing there. So here, so it represents path in which direction you are moving. So here, so we are moving from positive to negative. So EMF is negative. So in second case, you can go, you are going from negative to positive. That's why positive EMF. The end point is positive EMF. That is positive. Here end point is negative. So that's why negative EMF. And here you are moving along the current direction. You are moving along the current, here current direction. You are moving along the current direction. This is the path. Okay, if you are moving along the current direction, the IR term is negative. And if you are moving opposite to the current direction, so there is increase in potential, that's why plus IR. Okay, so potential is increasing, so that is plus IR, here minus IR, here path, so minus C and plus E. So EMF. Understood? So these are the points related to Kirchhoff laws. So I hope it is very clear. Right, next one. So we'll discuss about internal resistance and heating effects of electric current. Internal resistance and heating effect of electric currents. Internal resistance is nothing but when electron is moving in a conductor, okay, in the cell, it experience it experience it experience it experience some resistance. Okay, so when electron is moving in the conductor, it experience some resistance. Okay, so whatever you are taking EMF, that is not final, but there is an internal resistance. This is the cell resistance. So I am taking R. So here you can observe this is A and B. So potential equal to minus positive. This is the path. So along the current direction you are moving. E minus IR. Okay. So E minus IR. Understood or not? So negative to positive you are moving along the current direction. So IR term is negative. EMF is positive. So potential E equal V equal to E minus IR. That is about internal resistance. And coming to the next one is heating effect of electric current. Heating effect of electric current. Heating effects of electric current. Heating effects of electric current. Electric current. So now we can observe V equal to W by Q. V equal to W by Q. V equal to W by Q. From here W equal to VQ. You know rate of flow of charge is called current. So P equal to W by T. So VQ by T, that is nothing but V into Q by T, that is equal to VI. So energy P into T, that is nothing but VI into T. So V equal to IR. Then you can take H equal to IR into I into T, then H equal to I square RT. Heat produced in the conductor, heat produced in the conductor is directly proportional to square of current. Okay. Heat produced in the conductor is directly proportional to square of current. Heat produced in the conductor is directly proportional to resistance. Heat produced in the conductor is directly proportional to time. Okay. So I hope it is very clear. This is about heating effect of electric current. So next one. Next one. Next one. So you are going to the next topic is grouping of cells. Grouping of cells. Okay, grouping of cells. Let's start. So here we know already potential difference equal to work done by charge. So work done to bring unit positive charge from one point to another point within the conductor. Yes or no? So V equal to W by Q. So you can cross multiply W equal to V into Q. We know Q by T is I. So electrical. So P equal to rate of doing work. P equal to W by T. So we know W equal to V into Q. So W equal to V into Q by T. Yes or no? W equal to so you can see W by T, that is VQ by T. So we know Q by T is current, right? P equal to VI. Now, what are the energies given to the conductor? That is nothing but P into T. So P equal to we know VI. P equal to VI. So P equal to VI. Finally, you will get here P equal to VI. Electrical power. P equal to VA. So whatever the heat is, whatever the energy is given to the conductor, that will become in the form of heat. H equal to IR into I into T, H equal to I square RT. So heat produced in the conductor is directly proportional to square of current. Heat produced in the conductor is directly proportional to resistance. Heat produced in the conductor is directly proportional to time. So I hope it is very clear, right? So ray optics. Ray optics, okay. So I'll start. In the coming class, I'll discuss ray optics. Okay, so I hope it is very clear. This is about so heating effect of electric current. Next one we will discuss about. Grouping of cells. Grouping of cells. Grouping of cells. Okay. Grouping of cells. Now you can observe. So series combination, cells are connected in series. That is one cell resistor another resistor, another resistor. So that is connected to external resistance. Okay. So now you can observe E, R, E, R, E and R. Positive, negative, positive, negative, positive, negative. So current is flowing like this. This is the external resistance. Cells are connected in series combination. Cells are connected in series combination. Okay, so now net EMF equal to net EMF equal to NE net resistance, net internal resistance equal to net internal resistance, that is nothing but NR. So total resistance. So here you can observe, so all are connected in series, that's why I am taking NE. Total internal resistance, all are connected in series, internal resistance also series, so NR. Total resistance, so this also series combination, so that's why, so we'll write R plus, capital R plus, so capital R plus NR. Now, so current equal to net EMF by net or total resistance, we can say total resistance. Instead of writing net, we can write total resistance. Understood or not? Total resistance. I equal to NE is nothing but, so NE by R plus NR. Okay, this is about resistors are connected in series combination. Cells are connected. So we used to do resistors, right? Now cells are connected in series combination. Next we'll discuss about cells are connected in parallel combination. Cells are connected in parallel combination. Cells are connected in parallel combination, right? So see here, these are the cells. So now you can observe cells are connected in parallel combination. E and R of each cell is same. E and R of each cell is same. So now E and R of each cell is same. Then net EMF equal to E. because so in parallel combination EMF is same. So net internal resistance, net internal resistance equal to R by N. Normally resistance is 1 by Rp equal to N by R equal to R by N. So total resistance equal to, so R plus R by N. Now I equal to net EMF by total resistance. Okay, so net EMF is nothing but E. So total resistance is nothing but R plus R by N. That is current. Okay, I hope it is very clear. Understood or not? So, is it right? So, do you have any doubt in that? So, net EMF equal to E, net internal resistance equal to R by N, and so total resistance equal to R plus N by R by N. Oh, great. So, I equal to net EMF by total resistance. So, thank you so much. So, I hope it is very clear. These are the points. So, we discussed right from starting onwards. So, if you like the content, if you like the channel, if you like my explanation, so do like, share and subscribe to Student in the Brand. Share to your friends, ask your friends to join to the class. Inform to everyone, share to everyone as soon as possible, as much as possible. Okay. So thank you so much for joining and attending, listening and interacting with the class. So thank you so much. This is Vasavasa signing off. So do like, share and subscribe to Student in the Brand. Thank you. So only physics.